Hello everyone, I'm András Kovács. I'm going to talk about efficient elaboration with control definition unfolding. So there is a slight change compared to the program, because in the program I wrote evaluation, but then I thought that there are many things that I actually want to talk about, which is more related to elaboration. And fortunately, once again, I can say that all the previous talks talked a lot about elaboration, so now I can be double, triple thankful for everyone else who already explained what elaboration is. Okay, so what do we want? We want to fill holes during elaboration with nice terms, and we want to present nice terms to users during interaction. And unfolding all definitions everywhere is usually not nice. So we want to avoid that. But not unfolding anything can be also really bad in certain situations. So what we want to do is to preserve all these unfoldings. Essentially, we want to preserve the ability to make unfolding choices until we can actually make a good decision. And we also want to do this in an efficient way. So, like, for example, we don't want to recompute expensive computations from the scratch using a different unfolding mode. So let's start with some performance concerns related to unfolding. So there is this very classic Hindley-Milner type inference example, where we have a bunch of lets, and you can see here that I'm defining by let a pair of booleans, then I define another pair and another pair. And if we do type inference for this thing, then the elaboration output would also need to annotate these pairing constructors with the types, because they are some kind of polymorphic data constructors. So at each step, the size of the type involved here would double, and then in the end, we would get like 2 to the power of n size of types. So this is a very classic example for exponential inference in Hindley-Milner. And you might ask, well, who writes code like this? So why do we care? But apparently, ACDA users, including myself, so there are quite a few ACDA examples when we do some very crazy dependency type formalization, and actually we are doing some kind of essentially like a layering of indirections in dependency, which can result in exponential blowup. And we can also talk about quadratic elaboration. So quadratic elaboration is surprisingly common if we have fancy types. So here you can see an example where we have a cons, which is just, so this is some kind of pseudo-ACDA. So the cons is just a constructor for a vector of booleans. And here I have a definition for a vector where I'm consing together a bunch of truths to define some vector. And these underscores are just holes standing for the length of the rest of the vector. And if we do an elaboration and we unfold everything, then we will get a quadratic output, because here we have a suck, here we have a suck. And you can see that this doesn't quite fit, so I'm illustrating that this is too big in a sense. And sometimes people might actually want to copy-paste maybe a vector of size 100 into code, or maybe they have some tactics which output a vector of a size of 100. And there's also a related GHC, so there is a blog post about this, when writing essentially generic programs with heterogeneous list, exactly the same issue happens. And then the solution would be to have some kind of type level let, which can be used to introduce more sharing, so that we do not have to unfold all of these lengths or types in the elaboration output. Okay, so hash consing is kind of a well-known solution to prevent size explosions. But I say that hash consing is not sufficient, because hash consing doesn't know about beta expansions. So if you have like unary natural number, and then we might define 1 million, we can define 1 million in a very compact way using just a bunch of recursively defined operations. But if we actually evaluate it, the end result is incompressible by hash consing. And also hash consing, it doesn't really help with preserving unfoldings for the purpose of user interaction, but it can be still very useful to clean up very bad input. And it's kind of a general phenomenon is that whenever people write code, it's good input. But when tactics or programs write code, it can be really, really bad. And in that situation, hash consing can be still essential. Okay, so let's have a very basic setup. So this setup is is getting more and more popular, and I've been trying to make it more popular. But just to give a quick summary, so the core terms, so inside our system, there are core terms, the same way as in GHC, the same way as in Idris, essentially everywhere. This is a very standard thing to do. But here we say that core terms are viewed as immutable program code during elaboration. And the core terms can be evaluated into semantic values. And the semantic values are a bit richer. They contain more information. And such that all kinds of expensive computations can be implemented using on these kind of semantic values, most notably reductions, conversion, checking, and unification. And this is also the way WITS'24 works. And then there is a quotation operation which converts these semantic values back to terms. So in the end, the elaboration has to produce something which is a core term. So then we have to grab a bunch of values and convert them back to terms to be able to fill some holes in core terms. So this is kind of an interleaving of normalization by evaluation and elaboration, and I think this originates from theory Cocon. Yeah, so let's try to do some kind of super minimal normalization by evaluation with top-level unfolding control. And probably I will skip over some details, but maybe just let's do a quick overview. So we have terms. This is just essentially untyped lambda calculus extended with the notion of top-level variables. So there's some kind of implicit top-level scope with a bunch of definitions, and then we have top vars pointing into that, and the local vars are just the local bound variables of lambda calculus. But then we have the semantic values, and in the values, we have the neutrals. So the neutrals are just a local bound variable being applied to a list of things. So this spine is just a list of values. And this is just a stack application. So if you try to evaluate a bound variable, then it can get applied to a bunch of things. But of course, this evaluation cannot proceed further because it's being blocked by a variable. And then we have lambdas. So you can see that the body of the lambda is a function from value to value. And I'm writing some kind of pseudo Haskell here. You might even see the strict progba, which is a feature of pseudo Haskell. So this is a bit like we are working in strict Haskell, but the point is that almost everything is strict here, but at some places, laziness will be very important. So we have closures for lambdas. And then we have this extra thing, which I call V-unfold. And this is a delayed choice about definition unfolding. So this part of this data constructor, this top name and a spine, is a top definition, and the unfolding of this top definition is being delayed, but then it can get applied to a bunch of function arguments. So this is this spine. And the other thing, which is explicitly marked as being lazy, is the result of performing the unfolding and computing it until the next head construction in this language. So this is very similar to what was mentioned in Idris'24, but I'm not sure I fully understand it. There might actually be some difference between this implementation and that one. And then we can write an evaluator. And so we have an environment, we have a term, we do a case on the term. If it's a top-level variable, then we return this delayed unfolding choice. So we just return the top-level name together with an empty spine of applications, and then we lazily perform this top-level lookup. If we have a local variable, we just do a local lookup. So there's some kind of implicit top-level context here that I'm not writing here. If we have an application, we do some kind of semantic application, essentially an application of values to values. If we have a lambda, I just return a closure. And so the interesting part here is this value application, because, okay, so I'm trying to apply a value to a value. If the value is actually a lambda, I just call the function closure. If it is an unfolding, I just return a new unfolding such that I perform the application on both branches of this unfolding decision. On one side, I just extend the spine with the argument. On the other side, I just create a new thunk which recursively tries to perform this application operation on this value. So essentially what happens is that I am accumulating a bunch of chunks during evaluation such that at any point I am able to just choose one branch of this unfold or the other branch. But if I choose to look at both branches, computation will be, I would say, maximally shared between these two branches. So VNE. So this is a neutral value. So this is something which is being blocked by a bound variable. So if a computation is being blocked by a bound variable, there's nothing I can do. It just stays neutral forever. So this happens when I'm trying to evaluate expressions under a binder, for example, for a lambda binder. Okay. Okay. And then the other part of the story is going from values back to terms. And I call this operation quote. So maybe this is the more interesting part. I have essentially some supply of fresh variables, I have some supply of free variables, and then I can use this to generate fresh variables. I have this Boolean, which is actually the unfolding option. So if the Boolean is true, I'm performing all unfoldings at this point. If it's false, I don't do any unfolding, and then I can go from a value to a TM. So if I have a neutral value, I can essentially just generate a nested application as a term from it, because the neutral value just represents an iterated application to a bound variable. If I have a lambda, I can grab a fresh variable, and then I can create a term for the body of the lambda, and then recursively proceed. And if I have an unfolding, then I can do this if only unfolding. So if I'm doing unfolding, I'm just converting the unfolded result to something. And if I'm not doing the unfolding, then I'm just converting this part of this value into an iterated application. Okay, maybe there are some questions related to this? Yeah?
Yes. I don't understand maybe I'm just misreading this, but your v-unfold case says if unfold, then call quote again with ends unfold. Yes. Oh, okay, there's an extra v. That's what's different v. Okay, got it.
There's a v here. So this v is essentially the result of performing a top-level unfolding, and this is the result of not performing a top-level unfolding. If unfolding, I'm recursively quoting this result. Otherwise, I'm just creating the term and returning that.
I've kind of lost track of where you go from when you call eval and when you call quote. You define them both, and you can sort of go to and fro. But I've lost track of when you would call either.
We would call these, so I guess this is out of the scope of this talk, but in this style of elaboration, the eval and the quote is completely interleaved with the elaboration. So, for example, when we do a bidirectional type checking, sometimes we might want to know whether a checking type is a function type. And at that point, we need to have a value for the checking type and then match on it to see whether it is a function type or not. And that would be, okay, maybe it's not such a good example, but a very good example for calling this quote is when we solve a metavariable, because unification problem has values on both sides. And if we have a metavariable on one side and then a value on the other side, we need to convert the value to a term because we can only insert a term into the elaboration output. But the whole reason of doing this is essentially that for dependent type checking, we need to do conversion and we need to do reductions and evaluations for arbitrary functional programs because we have a dependently typed language. And we don't want to do some kind of naive substitution or some kind of slow stuff to do these reductions and these conversions. So we want to use essentially some kind of efficient abstract machine, which looks very much like a functional language interpreter. And we don't want to do expensive computation on terms ever. We want to evaluate terms into some semantic runtime object. And then when we actually need the terms, we want to convert back from the runtime object. I'm not sure how clear that is.
So can I just ask a follow-up, which is, you began with a slide about nested tuples and blah.
Mhm.
How does that connect with what you're just telling us now?
So this is kind of a very basic setup, but the way that this could connect, and actually it does, I mean, in some of the, I'm not sure, maybe this would also work in the new Idris too, as well. you can try. So the way that this would work, so what I showed is kind of not sufficient to handle this case, but it's just kind of part of the basic infrastructure. But the idea is that we want to view metavariable solutions as definitions, which we don't necessarily want to unfold, because if we unfold all of the meta solutions, we get the exponential blow-up. But if we don't always unfold them, we can just get a linear number of small size definitions, in which case this example can be still linear time elaborated. So we would just say that let some type equals bool per bool, another type equals pair of previous definition, and so on. So. Okay. Yeah. Yeah.
Unevaluated lambda and the evaluated lambda, and they want to have different bound variables for that.
I don't think anything like that comes up in this talk. So the two branches that we can take yield convertible values and terms. So they are always convertible. They live in the same environment as well. Okay. Okay, so yeah, probably I will need to speed up. But then, so an additional detail is that usually, so this was just a basic infrastructure, but usually we need to work with pairs of such values during elaboration and unification and conversion checking, because so these pairs of values, because sometimes we kind of force some values to weak at normal form, but when we do that, we do not want to forget where we started from. Because where we started from can be still very useful to present to the users and to quote into terms which are probably smaller than the unfolded versions. So that's why in the bidirectional elaboration algorithm, we have these gval is just a pair of values. And essentially, we have checking, inference, and unification. And here, the checking type is actually just a pair of values. And when we do inference, we are also returning such a pair of values. And then in unification, the unification also works in pairs of values. So for the left-hand side, we have a pair of values for the right-hand side. Because, for example, I have a meta variable on the left-hand side, and I have something on the right-hand side, and I want to do a meta solution. It might happen. I always want to be able to grab the least unfolded value, because then the least unfolded value usually will be the smallest. Okay, I'm not sure how clear it is, but you can see that this weak head normal forcing is quite simple. So we are just peeling off these unfolding nodes until we get something which is not an unfolding, but then we are losing information about some unfolding. So that's why we want to hold on to a least unfolded and the most unfolded version of values. And so this is an example for when we actually do want to unfold something during elaboration. So you can see here that elaboration input is just some map, some call to two map functions in some kind of Agda-like syntax. And the way that Agda works is that these map functions have some implicit arguments, and the implicit arguments will be top-level definitions. So they will be top-level functions. And the top-level functions all take all bound variables in the scope as argument, and this is called contextual metavariable, and this is used in Lean, I guess in Idris as well, and Agda. So GHC is the system where this is not being used. I guess in OCaml this is also not being used. Yeah, so we get a bunch of top-level functions for all the metavariables, and then the elaboration output, if we don't do any kind of unfolding or inlining or optimization on this particular piece of code, we just get a bunch of quite ugly function applications here in the output. And I do know that in Coq there is like some optimization to compress these application spines, but in general there is still a bit of overhead when we keep around these meta solutions. So what we really want to have is that because all of these meta solutions are completely trivial, we want to inline them. So we just inline them, and then we get some desired output, which looks pretty nice. And so this is the idea that when we are doing this elaboration of, I guess, dependently typed languages, we want to do some kind of early core optimization. And the two principles is that the user-written code should be preserved by elaboration, but the code which comes from elaboration or tactics should be optimized, ideally soon after it is being produced, because we do not want to hold on to lots of garbage, and we do not want to compute with terms which are kind of poor quality. But in my experience, a very simple and fast optimizations, like very basic inlining and let motion, and maybe eta reductions, make a big difference. So, for example, what I implemented in some system is that we take some kind of top-level binding block, like binding group, we elaborate it, we get a bunch of metas, but immediately after that, we do an inlining and optimization pass, so that the next thing that we elaborate can already refer back to the nice-looking code. And I have found that this is also super useful for getting a human-readable elaboration output during elaboration. And this is a major issue in Agda right now. So because in Agda, elaboration does this in a very naive way. So pretty much every meta solution is unfolded by default. We get a huge garbage as output, such that no one wants to read it. But because no one wants to read it, no one wants to develop and maintain pretty printing for it. And because we don't have a good pretty printing for it, no one even knows anymore what is in the elaboration output. So recently there were some issues when it turned out that Agda developers thought that some things are in the interfaces of modules, but the reality turned out to be quite different. So I think it's a very good kind of rule of thumb is that one of the most important points of this optimization is to make your elaboration output human readable. Okay, and I guess I don't really have time for anything else. I have a bunch of other things. Maybe just one very, very kind of a fun thing. So this is kind of a small and fun thing to mention at the very end. So what's wrong with this definition in Agda and elsewhere? We just have a record, and then we just have the fields. So this is just a record definition. We have we have to give definitions to each field. So what's the issue with this? And I think Agda users probably know that this pattern can behave very badly in type checking. Okay, so I guess it's already spoiler. Yeah, so the issue is that there's no way to share field definitions in elaboration. So if there's a metavariable in big defn, in the solution of that metavariable, all of these previous things must be unfolded because there's just no way to refer to them as a definition whatsoever. And I think the only way to actually fix this is to say that the construction of a record brings into scope each field name as a definition, which is kind of weird, but I don't see any other way to do it. So the veteran Agda users know that they have to use copatterns instead of this, because the copatterns actually require an elaboration to a top-level copattern matching definition, and it also makes it lazier to perform all these unfoldings, and then the performance can be actually fixed. But I think users should be able to actually write a local inlined record definition. I think it's a good feature to have. Okay, so and there are a bunch of related implementations. So like implementations which take some part of these features that I mentioned and implement them in some way. And so I also put this edges 2 here. Thank you.
So I think we have time for another question or two.
So I understand what you're proposing to keep the unfolded thing around and not unfold things too eagerly. So what I'm wondering is why do you need to keep this distinction between the semantic domain and the syntactic domain? Can't you just do everything in the same domain and just use sharing everywhere? And when you reconstruct an actual program term, you can reinsert a where clause, right, where you put all the sharing definitions.
Mm-hmm. So you say maybe, for example, let's just use maybe terms all the time?
Yeah, and use variables that
mm-hmm.
preserve all the sharing, which is the normal thing to do when you implement a unifier. You keep all the sharing, right?
So I think there's a reason. So if you look at like all of the functional programming language implementations like OCaml and Haskell, the way that the programs are being compiled and executed is not by doing substitution on terms.
Yeah.
So because that's horribly slow. Mm-hmm. So the idea here is almost exactly the same, is that instead of doing substitution on terms, we have abstract machines with some closures and environment, and then we can potentially do bytecode or machine code evaluation. Like for example, the Coq VM also uses this bytecode evaluation with closures, and that's way, way faster than trying to do substitution on terms. And I guess that's the basic idea.
Okay, I'm not proposing to do substitution on terms. I'm proposing to keep all the sharing you have. When you have a variable and it needs to be unified with something, you just keep track of this unification and you don't do a substitution, right? And then whenever you look back at this variable, you can look up the fact that it's been substituted.
I mean, so we need to run essentially arbitrary higher order programs during dependent type checking. Mm. So I don't see an easy way to make this proposal work with terms, and even if we try to do this sharing.
All right.
In the values, you had this v-unfold case, and later you again work with these glued values. Can you explain again why you need both?
So this stuff. So for example, it can happen. So we just want to do unification, and one of these values is actually something which is a nesting of v-unfolds, like a potentially a very deep nesting of v-unfolds. And then the way that we implement this unification algorithm is that maybe we force one side and we look at like, is this a metavariable? And if this is a metavariable, we want to solve it with the other side. But then, if we are doing this recursively, at any point we need to hold onto the most forced version when we peeled off all the unfolds, but we also need to hold onto the version which has not been unfolded, because if we just lose track of the least unfolded version of the value, then we lose this opportunity to generate like sharing in terms. I'm not sure if that's clear.
Yeah, I think so.
Okay.
Okay, so we're pretty much out of time. So thank you very much, András.